Imagine a single lonely atom floating in the void. Now imagine a trillion suns all swirling together in a majestic, silent dance. Now imagine the very first second of time itself, a moment of infinite energy from which everything we know emerged. What do all of these things have in common? They are all levels in the grand, quiet architecture of the cosmos. They are all stops on an immense ladder of understanding that stretches from our own familiar world to the very edge of reality. Tonight, we are going to climb that ladder. We will start at level 1, with the ground beneath our feet, and we will calmly, patiently make our way up to level 100, to the most profound and mind-bending concepts the universe has to offer. We begin our journey at level 1, the Earth. It seems like a simple starting point, but it is, in itself, a cosmic marvel. It is a world of impossible balance, a perfect combination of size, composition, and location. It is a rocky terrestrial planet, the third from its star, with a molten iron core that generates a protective magnetic field, shielding us from harmful solar radiation. Its surface is a dynamic tapestry of shifting continents, deep oceans, and a thick, nitrogen-rich atmosphere. It is, as far as we know, the only place in the entire universe where the complex chemistry we call life has taken hold and flourished into consciousness. It is the baseline, the control group, the quiet, beautiful anomaly from which we will measure all the strangeness to come. Its defining feature, the thing that makes it unique in our cosmic neighborhood, is the vast, shimmering presence of liquid water, the essential solvent for life itself. To be here is to have won a cosmic lottery of almost impossible odds. Our ascent continues to level 2, the Moon. This is our planet's constant, silent companion. It is a world painted in shades of gray and white, a place of profound silence and stillness. Its surface is a history book, covered in the craters and scars of billions of years of impacts. There are two distinct types of terrain. The brighter, heavily cratered areas are the lunar highlands, the ancient, original crust of the Moon, made of a light-colored rock called anorthosite. The darker, smoother areas are the lunar maria, or seas. They are not filled with water, but with dark volcanic basalt rock that flooded the low-lying basins after colossal impacts long ago. The Moon has no atmosphere to speak of, which means there is no wind, no weather, and no sound. A footprint left in its fine, powdery dust will remain perfectly preserved for millions of years, a quiet testament to a brief visit. It is a world without a sky, where the stars are hard, unwinking points of light in a perfect, absolute blackness. Now we turn our gaze to the center of our system, to level 3, the Sun. It is the engine of our world, a churning, incandescent sphere of plasma that contains over 99.8% of all the matter in the entire solar system. It is a G-type main sequence star, a yellow dwarf, though its true color is a brilliant, pure white. Its immense gravity holds all the planets in their orbits, and its ferocious energy, born from nuclear fusion in its core, bathes our world in the light and heat necessary for life. The core of the Sun is a place of unimaginable extremes, with temperatures of 15 million degrees Celsius and pressures billions of times that of Earth. Here, Every second, the sun fuses about 600 million tons of hydrogen into helium, converting 4 million tons of matter directly into pure energy. This energy then begins a long, slow journey outwards, taking tens of thousands of years to finally reach the surface and stream out into space as sunlight. The sun is not a gentle fire. It is a controlled, continuous, and colossal hydrogen bomb, a quiet, constant star whose stability is the single most important factor in our own existence. From the fire of the sun, we move outwards to a burnt and barren world for level 4, Mars. This is the red planet, our most explored and most intriguing neighbor. Its distinctive reddish hue comes from the vast amount of iron oxide, common rust, in its soil and dust. It is a world of grand, silent geology. It is home to Olympus Mons, the largest volcano in the solar system, a shield volcano so vast it would cover the state of Arizona, and so tall it stands 3 times higher than Mount Everest. It also boasts Valles Marineris, a system of canyons that dwarfs our own Grand Canyon, a colossal crack in the planet's crust that would stretch from one coast of the United States to the other. Today, Mars is a cold, dry desert world with an incredibly thin atmosphere, mostly made of carbon dioxide. But the quiet, tantalizing evidence left behind in its ancient rocks tells us that billions of years ago, it was a much warmer and wetter place with rivers, lakes, and perhaps even a northern ocean. It is the ghost of a once habitable world.
We continue our journey outward, past the asteroid belt, to the undisputed king of our solar system. This is level 5, Jupiter. It is a world on a completely different scale from the inner rocky planets. It is a gas giant, a colossal ball of hydrogen and helium so massive that it contains more than twice the mass of all the other planets in our solar system combined. It has no solid surface to stand on. If you were to descend into its atmosphere, you would pass through swirling cloud decks of ammonia ice and water ice into ever denser layers of gas until the pressure became so immense that the hydrogen gas itself is compressed into a bizarre state, a planet-spanning ocean of liquid metallic hydrogen. The rapid spin of this conductive fluid is what generates Jupiter's immensely powerful magnetic field, the strongest of any planet. The visible surface of Jupiter is a chaotic and beautiful tapestry of swirling storms and distinct cloud bands moving at incredible speeds. The most famous of these is the Great Red Spot, an anticyclonic storm wider than the entire Earth, which has been raging for at least 300 years. From the king of the planets, we drift to the jewel of the solar system at level 6, Saturn. The second largest planet, Saturn is another gas giant, similar in composition to Jupiter, but famous for its breathtaking system of rings. These rings are not solid objects. They are a vast, flat disk composed of countless individual particles of almost pure water ice. The particles range in size from tiny dust grains to boulders as large as a house. And while the ring system is incredibly wide, stretching for hundreds of thousands of kilometers, it is astonishingly, almost impossibly thin. In most places, the main rings are only about 10 meters thick. It is a structure of immense scale and incredible delicacy. Saturn itself is the least dense planet in our solar system. It is so light for its size that if you could find a bathtub large enough, it would float. At its north pole, it features one of the strangest and most beautiful storms we have ever seen, a persistent, perfectly six-sided jet stream known as the hexagon.
Our tour of the familiar now takes us to the smaller, more transient members of our solar system. We arrive at level 7, asteroids. These are the rocky, irregular bodies that are often called minor planets.
Most of them reside in the main asteroid belt, a vast, donut-shaped region of space between the orbits of Mars and Jupiter. They are not the remnants of a planet that was destroyed, but are instead the leftover building materials from the formation of the solar system that never managed to clump together to form a planet. The immense gravity of nearby Jupiter constantly stirred up this region, preventing a large world from ever coalescing. The asteroids range in size from pebbles to giants like Vesta. The largest of all, Ceres, is so large that its own gravity has pulled it into a spherical shape, and it is now classified as a dwarf planet. The asteroid belt, despite how it's shown in movies, is incredibly empty. The average distance between asteroids is millions of kilometers, making it a safe, if lonely, region to travel through. From the rocky leftovers, we move to the icy ones at level 8, comets. These are often called dirty snowballs, and that's a fairly accurate description. They are small bodies composed of a mixture of water ice, frozen gases like carbon dioxide and methane, and dust and rock. Most comets spend their entire lives in the cold, distant outer reaches of the solar system. But occasionally, a gravitational nudge will send one on a long, elliptical journey towards the sun. As the comet gets closer to the sun's heat, its ice begins to sublimate, turning directly into gas. This process releases a cloud of gas and dust that forms a large, hazy atmosphere around the comet's solid nucleus, called the coma. The solar wind then pushes this material away from the sun, creating the comet's two famous beautiful tails, a broad, curved dust tail and a straight, bluish ion tail. Comets are ancient, pristine relics from the birth of our solar system 4.6 billion years ago.
Now for a much more personal and fleeting phenomenon at level 9, meteors. Almost everyone has had the pleasure of seeing a shooting star, a brief, brilliant streak of light dashing across the night sky. These are not actually stars, of course. They are meteors. This phenomenon is caused by tiny particles of cosmic dust, called meteoroids, entering the Earth's atmosphere at incredibly high speeds. Most of these particles are no bigger than a grain of sand. As they hit our atmosphere, the immense friction and compression heats them up until they incandesce, burning up in a brilliant flash of light. On any given night, you can see a few of these. But several times a year, the Earth passes through the dusty debris trail left behind by a comet, which results in a meteor shower, where you can see dozens or even hundreds of shooting stars per hour, all appearing to radiate from the same point in the sky. It is a quiet, beautiful light show, our planet's atmosphere protecting us from the constant rain of tiny particles from space. Our final stop in this first tier of cosmic concepts brings us to the poles of our own planet. This is level 10, the aurora. This is the beautiful ethereal light show known as the aurora borealis in the north and the aurora australis in the south. For centuries, they were a source of myth and legend, seen as the spirits of ancestors or the reflections of celestial battles. We now know that they are a direct and beautiful manifestation of the connection between the sun and the earth. The sun is constantly sending out a stream of charged particles called the solar wind. Most of these particles are deflected by the Earth's magnetic field. But near the north and south poles, the magnetic field lines dip down and funnel these energetic particles into our upper atmosphere. As these solar particles collide with the oxygen and nitrogen atoms in our air, they excite them, causing them to glow in beautiful, shifting curtains of green, pink, and purple light. The aurora is the quiet, graceful dance of solar energy and planetary magnetism made visible.
All right, we have explored the most familiar sights of our cosmic home. Now, let's take our first real step up in scale and complexity. In this next tier of our journey, we will travel to the deep, cold outer reaches of our solar system and explore the fundamental physical concepts that govern everything we see. We begin at level 11, Uranus. This is the seventh planet from the Sun and the first of the ice giants. It is a world that for a long time was considered a bit of a mystery, mostly because it is so very far away and difficult to study. It is similar in size to Neptune, and its beautiful pale cyan blue color comes from the methane gas in its hydrogen and helium atmosphere, which absorbs red light and reflects blue light. When the Voyager 2 spacecraft flew by in 1986, it sent back pictures of a nearly featureless, serene, pale blue ball. But this calm exterior hides a deeply strange interior and a bizarre orientation. The most famous and unusual fact about Uranus is its extreme axial tilt. While Earth is tilted on its axis by a gentle 23.5 degrees, giving us our seasons, Uranus is tilted by a whopping 98 degrees. It is essentially orbiting the Sun on its side, like a rolling barrel. This means that for long stretches of its 84-year orbit, one pole faces the Sun continuously while the other is plunged into a decades-long, dark, and frigid winter. Now for level 12, Neptune. This is the eighth and most distant official planet in our solar system, the second of the ice giants. It is a world of a much deeper, more vibrant shade of blue than Uranus, and it is a much stormier place. Neptune is home to the fastest winds in the entire solar system, with supersonic jet streams whipping through its upper atmosphere at speeds of over 2,000 kilometers per hour. When Voyager 2 flew by, it saw a massive swirling storm system called the Great Dark Spot, similar to Jupiter's Great Red Spot. But unlike Jupiter's storm, which has been stable for centuries, Neptune's storms are transient. When the Hubble Space Telescope looked at Neptune a few years later, the Great Dark Spot was gone, and new storms had appeared elsewhere. It is a dynamic and incredibly windy world, a quiet puzzle of atmospheric physics so far from the Sun's heat.
Our journey continues outward, past the realm of the planets, to level 13, Pluto. For 76 years, Pluto was our beloved ninth planet. But as we began to discover more and more objects in the outer solar system that were similar in size to Pluto, it became clear that Pluto wasn't a lonely outpost, but simply the first discovered member of a vast new region of the solar system. In 2006, the International Astronomical Union officially reclassified it as a dwarf planet. But this change in status did not make it any less fascinating. When the New Horizons spacecraft flew by in 2015, it revealed a world of stunning complexity and beauty. It has vast, smooth plains of frozen nitrogen, like the famous heart-shaped glacier on its surface. It has towering mountains made not of rock, but of water ice that is as hard as granite at those frigid temperatures. It even has a thin, hazy nitrogen atmosphere. Pluto is not a dead, inert ice ball. It is a dynamic, geologically active, and incredibly complex world, the undisputed king of the Kuiper Belt. And that brings us to level 14, the Kuiper Belt. This is the vast, donut-shaped ring of icy objects that orbits the Sun beyond the path of Neptune. It is the third great region of our solar system, after the inner rocky planets and the outer gas and ice giants. It is a repository of ancient frozen relics from the very formation of the solar system. We believe there are hundreds of thousands of icy bodies larger than 100 kilometers across in the Kuiper Belt, and trillions of smaller comets. It is the source of most of the short-period comets that we see. In addition to Pluto, it is home to several other known dwarf planets, like Eris, which is actually more massive than Pluto, and Makemake and Haumea. It is a vast, cold, dark, and still largely unexplored frontier, the true outer edge of our planetary system.
But our solar system doesn't just stop at the Kuiper Belt. For level 15, we must take a final immense leap outwards into a theoretical, ghostly realm. This is the Oort cloud. The Oort cloud is a concept proposed by the astronomer Jan Oort to explain the existence of long-period comets, comets with orbits that take thousands or even millions of years to complete. He reasoned that there must be a vast spherical reservoir of these icy bodies surrounding our solar system at an incredible distance. The Oort cloud is thought to be a colossal, thick-walled sphere of trillions of icy comets, completely encompassing our sun and all the planets. Its scale is almost impossible to comprehend. It is thought to begin at a distance of perhaps a few thousand times farther from the sun than the Earth is, and it may extend outwards for over a light year, nearly a quarter of the way to the next nearest star. The objects in the Oort cloud are only very, very weakly bound by the sun's gravity. They can be easily disturbed by the gravitational pull of passing stars or the tides of the Milky Way galaxy itself. It is these gentle nudges that occasionally send a comet on its long, slow journey inwards towards our sun. We have never directly observed the Oort cloud. It is too vast, too dark, and too far away. It is a quiet, theoretical, and ghostly shell, the final true boundary of our solar system. Now that we have explored the full extent of our physical neighborhood, let's ascend to our next level by considering the fundamental forces and concepts that govern it. We begin with level 16, gravity. It is the most familiar of the universe's fundamental forces, yet it is also the strangest. It is the force that holds you in your chair, that holds the moon in orbit around the Earth, and that holds the entire Milky Way galaxy together. As described by Einstein's theory of general relativity, gravity is not a pull in the traditional sense. It is a curvature of space-time itself. Massive objects warp the fabric of space-time around them, and other objects simply follow the straightest possible path through this curved space. It is a force that is incredibly weak on small scales, but completely dominant on the largest scales of the cosmos. It is the quiet, invisible architect of the entire universe. From the force that governs motion, we now turn to the ultimate speed limit of that motion. At level 17, we have the speed of light. In a vacuum, light travels at a constant, unshakable speed of just under 300,000 kilometers per second. That's about 186,000 miles per second. It is the fastest that any energy, matter, or information can travel through the universe. Nothing can go faster. This is not just a technological limit. It is a fundamental law of physics woven into the very fabric of space-time. This ultimate speed limit has profound consequences. It means that information is not instantaneous. When we look at the sun, we see it as it was 8 minutes ago. When we look at the Andromeda galaxy, we see it as it was 2.5 million years ago. It also means that even with our most advanced technology, the dream of rapid interstellar travel is incredibly difficult. The distances are so vast that even traveling at the speed of light, a journey to the nearest star would take over 4 years. The speed of light is both the universe's ultimate messenger and its most profound gatekeeper. Because of this immense speed, we need a new yardstick to measure the cosmos. This brings us to level 18, a light year. This is one of the most common and sometimes most confusing units in astronomy. A light year is not a measure of time. It is a measure of distance. It is the distance that a beam of light can travel in one full Earth year. Given the speed of light, that distance is enormous.
A single light year is about 9.5 trillion kilometers, or about 6 trillion miles. It's a number so large that it is difficult for our minds to hold, but it is the only practical way to talk about the immense, quiet emptiness between the stars. The star Proxima Centauri is about 4.2 light-years away. The center of our Milky Way galaxy is about 26,000 light-years away, and the Andromeda galaxy is 2.5 million light-years away. The light year is the quiet language of cosmic distance. Our final two concepts in this tier bring us back to the influence of our own sun. At level 19, we have the solar wind. Our sun is not a static, quiet ball of fire. It is a dynamic and active star, and it is constantly breathing a stream of particles out into space. This is the solar wind. It is a tenuous flow of charged particles, mostly electrons and protons, that have been ejected from the sun's upper atmosphere, its corona, and are traveling outwards at speeds of hundreds of kilometers per second. This wind flows throughout the entire solar system, bathing all the planets in a constant stream of solar material. It is the solar wind that interacts with planetary magnetic fields to create auroras, and it is the force that pushes a comet's ion tail directly away from the sun. It is the sun's quiet, invisible breath, constantly shaping the environment of our solar system. This solar wind, in turn, creates our final exhibit in this tier, at level 20, the heliosphere. Just as the Earth has a magnetic field that creates a protective bubble around it called the magnetosphere, the Sun has a much, much larger one. The heliosphere is a colossal magnetic bubble that is inflated by the outward pressure of the solar wind. This bubble surrounds our entire solar system, extending far beyond the orbit of Pluto. It acts as a shield, protecting us from the harsh radiation of the interstellar medium, those galactic cosmic rays we've talked about. The boundary where the solar wind finally slows down and collides with the interstellar medium is called the heliopause. In 2012, the Voyager 1 spacecraft officially crossed this boundary, becoming the first human-made object to enter interstellar space. It has left the quiet, protective bubble of our sun and is now drifting in the great cosmic ocean between the stars. All right. We've explored our own solar system out to its ghostly, theoretical edge, and we've touched upon the fundamental laws that govern it. Now it's time for our next great ascent. We are leaving our home system behind and entering the vast, stellar realm. In this tier, we will take a quiet, biographical journey through the entire life cycle of a star, from its dusty conception to its quiet, fading death. We begin our story at level 21, stellar nurseries, more poetically known as nebulae. These are the places where stars are born. They are immense, beautiful, and incredibly diffuse clouds of interstellar gas and dust. Some nebulae are dark, cold clouds of molecular hydrogen, so thick they block the light from the stars behind them. These are the very earliest stages of star formation, but the most famous are the emission nebulae, like the Great Orion Nebula. These are regions where massive, young stars have already formed. The intense ultraviolet radiation from these hot newborn stars energizes the surrounding hydrogen gas, causing it to glow with a spectacular and characteristic pinkish-red light. A nebula is not a chaotic explosion. It is a quiet, vast, and surprisingly gentle place, a cosmic womb where gravity is slowly, patiently gathering the raw materials for the next generation of suns. Within these vast clouds,
we find our next stage at level 22, protostars. Deep inside the coldest, densest parts of a molecular cloud, gravity begins to pull the gas and dust together into clumps. As a clump grows more massive, its gravitational pull gets stronger and it starts to draw in more and more material from the surrounding cloud. This collapsing core of gas is a protostar. It is the embryonic stage of a star. It's not yet hot enough in its core for nuclear fusion to begin, but it is glowing. Its light comes not from fusion, but from the immense heat generated by its own gravitational collapse as the infalling material gets compressed and heated. A protostar is often shrouded in a thick disk of gas and dust from which a future planetary system might form. It is a star in its infancy, a quiet, glowing seed in the heart of a dark cloud. After millions of years of gathering mass, the pressure and temperature at the core of the protostar finally reach a critical tipping point, about 10 million degrees Celsius. At this moment, the star truly ignites. This brings us to level 23, main sequence stars. This is the long, stable, adult phase of a star's life. The ignition of nuclear fusion in its core creates a massive outward push of energy. This outward pressure perfectly balances the inward crush of gravity, and the star enters a state of equilibrium that it will maintain for most of its life. During this phase, the star is steadily fusing hydrogen into helium in its core. Our own Sun is a main sequence star, and it is about halfway through its roughly 10 billion year main sequence lifespan. The vast majority of stars we see in the night sky are main sequence stars. They come in many different sizes and colors, from the small, cool, dim red dwarfs to the massive, brilliant, hot blue giants. But they are all powered by the same quiet, steady process of hydrogen fusion. As we look at these stars, we find that many of them are not alone. This brings us to level 24, binary star systems. While our Sun is a solitary star, it seems to be in the minority. Astronomers have found that more than half of all Sun-like stars, and an even higher percentage of massive stars, exist in binary or multiple star systems. They are not single points of light, but two or more stars, born from the same cloud of gas, locked in a gravitational dance with each other. These systems can be incredibly varied. Some have two stars orbiting each other very closely, while others have companions that are very far apart. The existence of binary stars has profound implications for any planets in those systems, creating complex orbits and strange double sunsets. It's a quiet reminder that the typical solar system might not have one sun, but two or three.
Eventually, a star's long, stable adulthood comes to an end. When a star like our Sun has used up all the hydrogen fuel in its core, the fusion process stops. With the outward pressure gone, the core begins to collapse under its own gravity. This collapse heats the core up dramatically. This new heat then causes the outer layers of the star, which still contain plenty of hydrogen, to begin fusing in a shell around the core. This new burst of energy pushes the outer layers of the star outwards enormously. This is level 25, red giants. The star swells up to hundreds of times its original size, its surface cooling and turning a deep reddish-orange color. In about 5 billion years, our own Sun will become a red giant, its outer atmosphere expanding to engulf Mercury, Venus, and possibly the Earth itself. It is the beginning of the end for a star, a final, grand, and beautiful burst of glory before it dies. After the red giant phase, A star like our Sun doesn't explode. It dies a much quieter and more elegant death. This brings us to level 26, planetary nebulae. As the red giant star ages, its hold on its vast puffy outer layers becomes very weak. Gentle stellar winds begin to blow these outer layers of gas away into space. The star is, in effect, exhaling its own atmosphere. This shed material forms a beautiful, glowing, expanding shell of gas around the central dying star. We call these planetary nebulae, not because they have anything to do with planets, but because in early small telescopes, their round glowing shapes looked a bit like the disks of planets like Uranus or Neptune. They are some of the most beautiful objects in the night sky, with intricate shapes like rings, bubbles, and hourglasses. They are the quiet, colorful ghosts of dead, sun-like stars. And what is left behind at the center of a planetary nebula? This is level 27, white dwarfs. After a sun-like star has puffed away its outer layers, its hot, dense core is left behind. This is a white dwarf. It is an incredible object. It contains about half the mass of the original star, but it has been compressed down into a sphere about the size of the Earth. The density is immense. A single teaspoon of white dwarf material would weigh several tons. The white dwarf is no longer producing any new energy through fusion. It is just the incredibly hot, leftover ember of the star's core. It shines with a brilliant white light, not because of fusion, but because it is still radiating away all the heat from its former life. Over billions and billions of years, a white dwarf will slowly cool down and fade, eventually becoming a cold, dark, black dwarf, the final, quiet corpse of a star. Our universe is not yet old enough for any black dwarfs to have formed. Now, what about the stars that are much smaller than our Sun? This brings us to level 28, brown dwarfs. These objects are often called failed stars. They are the runts of the stellar litter. They form in the same way as stars, from a collapsing cloud of gas and dust, but they never quite get massive enough to ignite true, sustained hydrogen fusion in their cores. The cutoff point for a star is about 8% of the mass of our Sun. Anything less than that, and the core just doesn't get hot enough or dense enough for fusion to start. These brown dwarfs are more massive than planets, typically 13 to 80 times the mass of Jupiter, but they are not quite stars. They glow faintly, not from fusion, but from the residual heat of their formation, and they are often detected by their infrared rather than visible light. They are the quiet, lukewarm middle ground between a giant planet and a small star. From the failed stars, we now turn to the most successful and most common stars of all. At level 29, we have red dwarfs. These are the smallest and coolest type of main sequence star. They are much less massive than our Sun, and they burn through their hydrogen fuel incredibly slowly and efficiently. While a star like our Sun has a lifespan of about 10 billion years, a red dwarf can live for trillions of years. Since the universe is only about 13.8 billion years old, not a single red dwarf that has ever existed has had enough time to die yet. Every single one is still in its stellar infancy. They are the quiet, dim, and incredibly long-lived majority of the stellar population. Because they are so dim, we can't see any of them with the naked eye, but they are all around us. The nearest star to our Sun, Proxima Centauri, is a red dwarf. Finally, to close out our tour of the lives of stars, we come to level 30, stellar classification. When you look at the stars, you see a variety of colors and brightnesses. To make sense of this, astronomers in the late 19th and early 20th centuries developed a system to classify stars based on their temperature, which is closely related to their color. This system is known as the Morgan-Keenan system, and it organizes stars into a sequence of letters: O, B, A, F, G, K, M. O-type stars are the hottest, most massive, and bluest stars. M-type stars, the red dwarfs, are the coolest and smallest. Our Sun is a G-type star, somewhere in the middle. Generations of astronomy students have learned this sequence using the famous mnemonic, "Oh, be a fine girl or guy, kiss me." It is the quiet, orderly language that astronomers use to bring a sense of classification and understanding to the vast and varied zoo of stars in our galaxy.
All right, we've explored the long, quiet, and mostly stable lives of stars like our Sun. Now, let's take another step up our ladder of cosmic concepts and enter a much more violent and extreme realm. In this tier, we will explore the spectacular deaths of massive stars and the bizarre, powerful objects they leave behind. We begin at level 31, supernovae. When a star that is much more massive than our Sun runs out of fuel, it does not gently puff away its outer layers like a sun-like star. It dies in a colossal explosion called a supernova. As we've discussed, the iron core of the massive star collapses in less than a second. This collapse triggers a shockwave that rips through the star, blasting its material out into space at incredible speeds. For a few weeks, a single supernova explosion can outshine its entire host galaxy, releasing as much energy as our Sun will in its entire 10 billion-year lifetime. It is one of the most energetic and violent events in the entire universe. These explosions are not just beautiful, they are essential for life. It is in the heart of these explosions that elements heavier than iron are forged, and it is the shockwave that spreads all the elements, both light and heavy, throughout the galaxy, providing the raw materials for new stars, new planets, and new life. What is left behind after a supernova? If the original star wasn't too massive, the collapsed core will stabilize to form our next object at level 32, neutron stars. A neutron star is one of the strangest and most extreme forms of matter in the universe. It is the super-dense corpse of a massive star. It contains more mass than our entire Sun, but it has been crushed down by gravity into a perfect sphere only about 20 kilometers in diameter. It is a stellar core the size of a city. The density is almost beyond comprehension. A single teaspoon of neutron star material would weigh billions of tons. The gravity is so immense that the star is made almost entirely of pure neutrons, packed together as tightly as the laws of physics will allow. It is a single, giant atomic nucleus, a quiet, city-sized monument to the power of gravity. These neutron stars are often spinning incredibly rapidly, a remnant of the spin of the original star, concentrated into a much smaller object. This brings us to level 33, pulsars. A pulsar is a type of rapidly spinning neutron star that has a very powerful magnetic field. This magnetic field is tilted relative to the star's rotational axis. As the star spins, its magnetic field funnels charged particles into powerful beams of radiation that shoot out from its magnetic poles. The result is a cosmic lighthouse. If one of these beams happens to sweep past the Earth as the star rotates, our radio telescopes will detect a brief, perfectly regular pulse of radio waves. Some pulsars spin hundreds of times every second, creating a radio pulse with a regularity that is more accurate than an atomic clock. When they were first discovered in 1967 by Jocelyn Bell Burnell, the signal was so precise and so unnatural looking that the astronomers briefly nicknamed the source LGM-1 for Little Green Men, half-jokingly considering that it might be a signal from an alien civilization. We now know they are the quiet, rhythmic heartbeats of dead stars. If the collapsing core of a supernova is even more massive, above a certain limit, then not even the pressure of the neutrons can stop the force of gravity. The core will continue to collapse indefinitely. This creates our next object at level 34, stellar mass black holes. As we know, a black hole is an object whose gravity is so strong that nothing, not even light, can escape. The core of the dead star collapses down to a point of infinite density, a singularity, and it creates an event horizon around it, a one-way door from which there is no return. These stellar mass black holes, formed from the death of a single star, are typically a few to a few dozen times the mass of our Sun. They are the quiet, invisible ghosts that massive stars leave behind, scattered throughout our galaxy.
Now let's look at the bigger siblings of these stellar corpses. At level 35, we have quasars. In the early days of radio astronomy, scientists found incredibly bright, star-like sources of radio waves, but they couldn't figure out what they were. They were called quasi-stellar radio sources, which was shortened to quasars. We now know what they are, and the reality is incredible. A quasar is not a star. It is the intensely luminous, active core of a very young, very distant galaxy. And the engine powering a quasar is a supermassive black hole, billions of times the mass of our Sun, that is in the process of a feeding frenzy. In the early gas-rich universe, huge amounts of gas and dust were funneled towards the centers of young galaxies. This material would form a massive superheated accretion disk around the central black hole. As this material spiraled into the black hole, the intense friction and gravitational energy would cause the disk to shine with a brilliance that could outshine the entire host galaxy by a factor of thousands. Quasars are the brightest objects in the universe, beacons of light from the cosmic dawn, powered by the most destructive force in nature. Our next level, level 36, takes us back to the life of a star, but the most massive stars of all. These are the red supergiants. A star like Betelgeuse in the constellation Orion is a perfect example. It is so enormous that if you replace it in the center of our solar system, its outer atmosphere would extend out past the orbit of Jupiter. It is a colossal, puffy, and relatively cool star in the final stages of its life. It is fusing heavier and heavier elements in its core and will, in the relatively near cosmic future, explode as a spectacular supernova, an event that will be bright enough to be visible during the day from Earth. These quiet, dying titans are the time bombs of our galaxy. From the biggest stars, we now turn to the biggest explosions. At level 37, we have gamma-ray bursts, or GRBs. For a few brief moments, these are the most powerful and luminous events in the entire universe. A typical GRB releases as much energy in a few seconds as our Sun will in its entire 10 billion year lifetime. They come in two main flavors. The long bursts, lasting more than 2 seconds, are thought to be caused by hypernovae, the collapse of extremely massive, rapidly spinning stars into black holes. The short bursts are thought to be caused by the collision and merger of two neutron stars. What makes them so powerful is that the energy is not released in all directions. It is focused into two narrow, diametrically opposed jets of pure energy, traveling at nearly the speed of light. They are cosmic sniper rifles. If one of these jets were aimed directly at the Earth, even from a galaxy halfway across the universe, it could have a devastating effect on our atmosphere. They are the universe's ultimate expression of violent power. Our next exhibit, at level 38, is a familiar one, but it belongs in this violent company. This is the magnetar. As we've explored in great detail, a magnetar is a very rare and special type of neutron star, born from a star that was both massive and rapidly spinning. It is home to the most powerful magnetic field in the entire universe, a field a quadrillion times stronger than Earth's. This immense magnetic energy cannot be contained forever.
It causes the star's solid crust to crack in starquakes, which in turn triggers violent, unpredictable outbursts of X-rays and gamma rays. The giant flare from a magnetar is one of the only events that can rival a GRB in terms of sheer power. They are the universe's ultimate expression of violent power.
Now, for level 39, we look at the structure that powers many of these violent events. This is the accretion disk. An accretion disk is not a solid object, but a swirling, rotating disk of gas, dust, and other material that forms around a massive gravitational object, like a white dwarf, a neutron star, or a black hole. As material is pulled towards the central object, its own spin or angular momentum causes it to flatten out and form this disk structure. The physics of an accretion disk are incredible. The material closer to the center orbits much faster than the material farther out. This difference in speed creates immense friction between the layers of gas, and this friction generates a tremendous amount of heat. The inner parts of an accretion disk around a black hole can reach temperatures of millions of degrees, causing them to shine brilliantly in X-rays. It is this light from the accretion disk, the light from the matter being heated to extreme temperatures as it falls to its doom, that allows us to see and study black holes. The accretion disk is a place of both creation and destruction. In the case of a young star, the accretion disk is where planets are born, as the dust and gas slowly clump together. In the case of a black hole, it is the final, brilliant farewell of matter before it crosses the event horizon and disappears from the universe forever. It is a quiet, swirling vortex at the edge of oblivion. Our final stop in this gallery of cosmic violence is a concept rather than an object. At level 40, we have the event horizon. This is the defining feature of a black hole. It is not a physical surface you could touch. It is a purely theoretical one-way boundary in space-time. It is the point of no return. The event horizon is located at a specific distance from the central singularity, known as the Schwarzschild radius. At this distance, the curvature of space-time becomes so extreme that the escape velocity, the speed needed to get away, becomes greater than the speed of light. Since nothing can travel faster than light, nothing that crosses the event horizon can ever get back out. It is the ultimate prison wall, a quiet, perfect sphere of blackness that forever hides the mysteries within.
All right, we have explored the lives and deaths of individual stars. It's time to zoom our perspective out once more, to appreciate the grand structure in which all these stars live. We are now entering the tier dedicated to our own home galaxy, the Milky Way. We begin at level 41, the spiral arms. Our galaxy is a beautiful spiral galaxy, but its arms are not static structures like the spokes on a wheel. They are dynamic, transient patterns, waves of creation sweeping through the galactic disk. As we've discussed, these arms are density waves, a kind of cosmic traffic jam where clouds of gas and dust are compressed, triggering the birth of new stars. This is why the spiral arms are so bright and have a distinct bluish tint. They are filled with the brilliant, hot, young O and B-type stars that have only recently been born and have not had time to drift away. Our own Sun is currently located in a smaller partial arm called the Orion Arm, a quiet suburban street off the main galactic highway. From the bright, youthful arms, we move inward to level 42, the galactic bulge. This is the dense, spheroidal hub at the center of our galaxy. It is a much older and more settled place. Unlike the orderly, circular orbits of the stars and the spiral arms, The stars in the bulge move on more random, elongated, and inclined orbits, like a buzzing swarm of cosmic bees. The stars here are mostly old, yellow, and red stars, giving the bulge a soft golden glow. Star formation in this region largely finished billions of years ago. At its heart, the density of stars is immense, and the night sky from a planet in the bulge would be a breathtaking, brilliant tapestry of light. At the very heart of this central bulge, we find level 43, the galactic bar. For a long time, we thought the Milky Way was a simple spiral galaxy, but more recent observations, especially with infrared telescopes that can peer through the obscuring dust, have revealed that our galaxy's bulge is not perfectly round. It is an elongated, bar-shaped structure of old reddish stars stretching for about 27,000 light-years from end to end. This makes our galaxy a barred spiral galaxy. This bar is not just a pretty feature, it's a dynamic engine. Its powerful gravity is thought to act like a giant funnel, channeling gas and dust from the inner parts of the galaxy towards the very center, potentially feeding the monster that lurks there. And that monster is our next stop, at level 44, Sagittarius A star. Pronounced Sagittarius A star and often abbreviated SGRA*, this is the name of the supermassive black hole that resides at the absolute gravitational center of the Milky Way. Every single star in our galaxy, including our own sun, is on a long, slow journey orbiting this central point. By tracking the incredibly fast orbits of stars very close to the center, astronomers have been able to calculate its mass with great precision. It weighs in at about 4.3 million times the mass of our sun. And all of that mass is packed into a region smaller than the orbit of Mercury. Despite its immense mass, SGRA* is currently a very quiet black hole. It is not actively feeding on large amounts of material, so it is not shining brightly like a quasar. It is a sleeping giant at the heart of our home. Now let's move from the center to the most ancient parts of our galaxy. At level 45, we find the globular clusters. These are some of the most beautiful and oldest objects in the entire galaxy. A globular cluster is a dense, perfectly spherical swarm of hundreds of thousands or even millions of very old stars. They are all tightly bound together by their mutual gravity. These clusters are not found within the flat disk of the galaxy where we live. Instead, they orbit the galaxy in the vast outer region known as the halo. They are like ancient glittering satellites, following long elliptical paths. The stars within a globular cluster are all very old, having formed at the same time over 10 to 12 billion years ago, making them relics of the very dawn of our galaxy's history. The density of stars at their core is incredible, thousands of times greater than in our own stellar neighborhood. This ancient swarm of globular clusters is just one part of a much larger, more ghostly structure. This is level 46, the stellar halo. The halo is a vast, roughly spherical cloud of very old, very sparse stars that surrounds the entire Milky Way disk. If the main disk is like a bright, bustling city, the halo is its vast, quiet, and almost empty countryside. The stars here are ancient, metal-poor, first-generation stars, and they are spread incredibly far apart. The halo itself is thought to be the result of galactic cannibalism. It is made up of the shredded, ghostly remnants of smaller, dwarf galaxies that the Milky Way has captured and torn apart over billions of years. It is our galaxy's quiet, invisible, and very ancient attic.
Our galaxy is not alone in the void. This brings us to level 47, the local group. Our Milky Way is one of the two dominant members of a small village of galaxies, a gravitationally bound cluster containing about 80 known members. The other dominant member is our big sister, the Andromeda Galaxy. The rest of the members are much smaller dwarf galaxies, most of which are in orbit around either the Milky Way or Andromeda. This entire cluster, our cosmic family, is about 10 million light-years across. And the big sister of that family is our next level, level 48, the Andromeda Galaxy. Also known as M31, this is our nearest major galactic neighbor, located about 2.5 million light-years away. It is the most distant object you can see with the naked eye. It is a beautiful spiral galaxy, much like our own, but it is significantly larger, with a disk that is perhaps twice the diameter of the Milky Way's, and containing up to 1 trillion stars. And it holds a strange and interesting distinction in our night sky. While almost every other galaxy we see is moving away from us due to the expansion of the universe, Andromeda is heading directly towards us at a speed of over 100 kilometers per second. This is because our mutual gravity is strong enough to overcome the cosmic expansion. In about 4.5 billion years, our two galaxies are destined for a spectacular, slow-motion collision and merger.
Huddled around our own galaxy are its smaller companions. This is level 49, satellite galaxies. These are small dwarf galaxies that have been captured by the Milky Way's immense gravity and are now in orbit around us. The two most famous of these are the Large and Small Magellanic Clouds, which are visible as faint cloudy patches in the night sky of the southern hemisphere. They are irregular dwarf galaxies, each containing a few billion stars. They are currently making a close pass to the Milky Way, and our galaxy's gravity is pulling long streamers of gas away from them. Eventually, over billions of years, they will likely be completely torn apart and absorbed into our own galaxy. We are cosmic cannibals in the process of consuming our closest neighbors. Our final stop in this tier, at level 50, is a more conceptual one. It's the idea of the galactic habitable zone. Just as there is a Goldilocks zone around a star where a planet can have liquid water, some scientists propose there might be a similar habitable zone within the galaxy itself. If you are too close to the galactic center, it's a very dangerous neighborhood. The density of stars is high, meaning the chance of a nearby supernova sterilizing your planet is much greater. The radiation from the central supermassive black hole is also intense. But if you are too far out, in the distant suburbs of the galaxy, there is a different problem. The stars there tend to be older and have a lower concentration of heavy elements, or metals. These heavy elements are the necessary building blocks for rocky planets and for life itself. The galactic habitable zone is the quiet, safe, and resource-rich ring in between these two extremes, a cosmic sweet spot where a planet like Earth is most likely to form and to survive long enough for complex life to evolve.
All right, we have explored our own vast galaxy in detail. It's time to ascend again, to zoom our perspective out even further and appreciate the incredible diversity of galaxies that populate the wider universe. Welcome to the Galactic Zoo. We begin at level 51, with the most common type of galaxy in the universe, especially among the most massive galaxies. These are the elliptical galaxies. Unlike the beautiful flat spinning disks of spiral galaxies, ellipticals are huge football-shaped or spherical swarms of stars. They are much more three-dimensional. The stars within them are generally very old, shining with a soft yellowish-red light. And they are on completely random orbits, like a buzzing swarm of bees in a hive.
Elliptical galaxies are thought to be the end product of galactic evolution. They are red and dead, meaning they have used up almost all of their gas and dust and are no longer forming any new stars. They're the quiet, retired elders of the cosmic city. Next, at level 52, we have a transitional type of galaxy. This is the lenticular galaxy. Lenticular just means lens-shaped. These galaxies are a beautiful hybrid between a spiral and an elliptical. They have a large central bulge and a flattened disk just like a spiral galaxy, but they have no visible spiral arms. Like elliptical galaxies, they have very little gas and dust and are made up of mostly old, aging stars. They are thought to be spiral galaxies that have used up all of their star-forming fuel, causing their bright spiral arms to fade away, leaving behind just the underlying disk and bulge. They are a quiet snapshot of a galaxy in its middle age after its youthful star-forming period is over.
From the orderly galaxies, we now turn to the chaotic ones. At level 53, we find the irregular galaxies. As their name suggests, these galaxies have no defined shape at all. They are messy, clumpy, and chaotic collections of stars and gas. They are often rich in gas and dust and are undergoing intense bursts of star formation. Many irregular galaxies are thought to be the result of gravitational interactions or collisions with other galaxies. The tidal forces from a close pass with a larger galaxy can disrupt a smaller galaxy's shape, tearing it apart and triggering a wave of chaotic star birth. Our own neighbors, the Large and Small Magellanic Clouds, are examples of irregular galaxies, their shapes distorted by the powerful gravity of the Milky Way. Next, at level 54, we have one of the rarest and most beautiful types of galaxy. This is the ring galaxy, and our primary example is the famous Hoag's object we discussed earlier. These galaxies, with their bright, young, blue ring of stars surrounding an old yellow core, are a profound cosmic puzzle. As we learned, they are thought to be the result of a bullet galaxy scoring a direct bullseye hit on the center of a larger disk galaxy, creating a ripple of star formation that expands outwards. They are a quiet, fleeting, and almost perfectly geometric testament to the violence of galactic collisions. This brings us to level 55, the starburst galaxies. These are galaxies that are currently undergoing a period of star formation at an absolutely furious rate. A normal galaxy, like our Milky Way, might form a handful of new stars every year. A starburst galaxy can be forming hundreds or even thousands of new stars per year. They are some of the brightest and most luminous objects in the universe. This intense burst of star formation is usually triggered by a galaxy merger or collision. The collision of the two galaxies' gas clouds creates a massive shock wave that compresses the gas and sparks a galaxy-wide firestorm of creation. This phase is spectacular, but short-lived. The galaxy will quickly burn through all its available gas and then settle down into a quieter, more sedate existence.
Now, let's look at galaxies that are not just bright from stars, but from their very hearts. At level 56, we find active galactic nuclei, or AGN. These are galaxies that have an incredibly bright, compact core that can sometimes outshine the light of all the billions of stars in the galaxy combined. The engine powering an AGN is a supermassive black hole that is in the process of a massive feeding frenzy. As we discussed with quasars, which are the most luminous type of AGN, a huge amount of gas and dust is spiraling into the central black hole, forming a brilliant superheated accretion disk. This disk shines with incredible intensity across the entire electromagnetic spectrum. Some AGN also produce those colossal relativistic jets that shoot out from the poles of the black hole at nearly the speed of light. AGN are a window into the most violent and energetic processes in the universe, all powered by the quiet, relentless force of gravity from a single central object. These galaxies are not isolated. They are part of a grander structure. This brings us to level 57, galaxy clusters. Galaxies themselves are gravitationally bound into groups. Our local group is a very small and modest example. A true galaxy cluster is a colossal structure containing hundreds or even thousands of large galaxies, all orbiting each other in a deep shared gravity well. The space between the galaxies in a cluster is not empty. It is filled with a vast, incredibly hot cloud of intergalactic gas that can only be seen with X-ray telescopes. Galaxy clusters are the great cities of the universe, the most massive, gravitationally bound objects we know of. And even these clusters are part of an even grander structure. At level 58, we have galaxy superclusters. A supercluster is a massive chain or wall-like structure composed of many galaxy clusters and groups, all loosely connected by gravity. Our local group is part of the Virgo supercluster, and the Virgo supercluster is in turn just one small lobe of an even larger structure called the Laniakea supercluster. These superclusters are some of the largest known structures in the entire universe.
The arrangement of these superclusters leads us to our next level of understanding. At level 59, we have the cosmic web. When we map out the locations of millions of galaxies in 3 dimensions, we find that they are not spread out randomly. They are arranged in a vast, beautiful, and intricate web-like pattern that fills the entire universe. This cosmic web consists of dense, long filaments made of thousands of galaxies, which meet at even denser nodes, the galaxy clusters. Surrounding these filaments and clusters are the vast, almost empty regions we know as voids. This beautiful, sponge-like structure is a direct and visible consequence of the tiny quantum fluctuations that were present in the very early universe, stretched to colossal proportions by cosmic expansion. It is the grandest pattern in all of nature. Finally, for level 60, we look at the process that builds this web. This is the process of galaxy mergers. Galaxies are not static islands. They are dynamic objects that are constantly interacting with each other through gravity. Over the vast time scales of the cosmos, galaxies frequently collide and merge. When 2 spiral galaxies, like our Milky Way and Andromeda, collide, their beautiful disk structures are destroyed by the violent tidal forces. Their gas clouds slam into each other, triggering a massive starburst. And over billions of years, the 2 galaxies will settle down and merge into a single, much larger and more disordered elliptical galaxy. This process of hierarchical merging is how we believe the largest galaxies in the universe are built. It is a quiet, slow-motion ballet of cosmic creation and destruction happening all around us all the time.
All right. We have taken a grand tour of the visible universe, from the smallest moons to the largest superclusters of galaxies. Now we must take a deep breath and ascend to a new, much stranger, and much more mysterious tier. We are now entering the realm of the invisible. This tier is dedicated to the quiet, ghostly components of our universe that we cannot see, but whose presence we can feel. The great dark mysteries of cosmology. We begin at level 61 with the most famous of these mysteries, dark matter. As we've discussed, all the normal, visible matter that makes up the stars, the planets, and us accounts for only about 15% of the total matter in the universe. The other 85% is this strange, invisible, and completely unknown substance. The story of its discovery is a quiet tale of scientific perseverance championed by the astronomer Vera Rubin. In the 1970s, she meticulously measured the rotation speeds of spiral galaxies. She found that the stars on the outer edges of these galaxies were moving far too fast. The gravity from the visible matter wasn't nearly enough to hold them in their orbits. The galaxies should have flown apart. She concluded that the galaxies must be embedded in a vast, invisible halo of some other kind of matter, a dark matter halo, that was providing the extra gravitational glue. Her work was met with skepticism for years, but the evidence she uncovered was undeniable. Our next level, level 62, is the even more dominant and even more mysterious component of our universe, dark energy. For most of the 20th century, we assumed the expansion of the universe, started by the Big Bang, was being slowed down by the force of gravity. But in the late 1990s, two teams of astronomers studying distant supernovae made the shocking discovery that the expansion is not slowing down, it is speeding up. There is a mysterious, repulsive force woven into the fabric of space-time itself that is pushing the universe apart. We call this force dark energy. And when we do the cosmic accounting, it turns out that this strange energy makes up about 70% of the entire mass energy content of the universe. Together, dark matter and dark energy account for 95% of everything. Our entire reality, our entire science, is based on the 5% of the universe that we can actually see. We are, in a very real sense, just the foam on the surface of a vast, dark cosmic ocean.
So, how do we see these invisible things? One of the most powerful tools we have is at level 63, gravitational lensing. This phenomenon is a direct prediction of Einstein's theory of general relativity, which tells us that massive objects curve the fabric of space-time around them. And as light from a distant object travels through this curved space, its path gets bent, much like light passing through a glass lens. This effect is a beautiful and powerful tool for astronomers. When we look at a massive galaxy cluster, the gravity of the cluster, including its huge halo of dark matter, can bend and magnify the light from even more distant galaxies located behind it. This can create beautiful, distorted arcs of light, or even multiple smeared images of the same background galaxy. By measuring the amount of this lensing, we can create a map of all the mass in the cluster, both visible and invisible. And these maps have confirmed with stunning precision the existence and distribution of dark matter. It's a way of seeing the invisible by observing its quiet, powerful effect on the light that passes by. From the invisible matter that fills the universe, we now turn to the great voids that empty it. At level 64, we revisit the Boötes void. This great nothing is a profound puzzle. Our models of the cosmic web predict that voids should exist, but they don't predict that they should be this large or this empty. The sheer scale of it is hard to comprehend. It is 330 million light-years in diameter. It is so large that if you were traveling at the speed of light, it would take you longer than the entire age of the dinosaurs to cross it. The handful of galaxies that exist inside it are arranged in a strange, lonely tube-like filament, as if they are huddling together in the vast, quiet emptiness. The Boötes void is a quiet, humbling reminder of the lumpy, non-uniform nature of our cosmos, a place where the silence and the darkness are on a scale that challenges our imagination. Our next level, level 65, introduces us to the ghost particles of the universe, neutrinos. Neutrinos are fundamental subatomic particles that are created in the hearts of stars and other high-energy cosmic events. They are incredibly abundant. Trillions of them from our own sun are passing through your body every single second. But they are almost impossible to detect. This is because they barely interact with normal matter at all. They have a tiny amount of mass, but no electric charge, so they can pass through entire planets, stars, and galaxies as if they were empty space. They are the ultimate cosmic ghosts. To detect them, scientists have to build enormous detectors deep underground, shielded from all other forms of radiation. These detectors are essentially giant tanks filled with thousands of tons of ultra-pure water or other materials, lined with incredibly sensitive light detectors. Very, very rarely, one of the trillions of neutrinos passing through the tank will happen to bump into an atom, creating a tiny, faint flash of light that the detectors can pick up. By studying these ghostly messengers, we can learn about the nuclear fusion processes happening deep inside our sun, or about the core collapse of a distant supernova. From the ghosts we can barely see, we turn to the whispers we can barely feel. At level 66, we have gravitational waves. As we've discussed, these are ripples in the fabric of space-time itself, created by the most violent events in the cosmos, like the collision of two black holes or two neutron stars. They are not a form of light. They are a literal stretching and squeezing of space and time. As a gravitational wave passes by, it causes everything in its path to expand and contract by a minuscule amount. For the first gravitational wave we ever detected, the amount of stretching was thousands of times smaller than the width of a single proton. Detecting this almost impossibly small vibration is one of the greatest technological achievements in human history, giving us a brand new way to listen to the quiet, deep rumbles of the universe.
So what is dark matter actually made of? At level 67, we explore the leading candidates, WIMPs and axions. These are two of the main hypothetical particles that physicists believe could be the constituent of dark matter. WIMPs stands for weakly interacting massive particles. The theory suggests these are heavy particles left over from the early universe that, as their name suggests, interact very weakly with normal matter, primarily through gravity and the weak nuclear force. This would explain why we can't see them. The massive underground detectors we talked about are primarily designed to try and catch the faint signal of a WIMP bouncing off a normal atom. Axions are another much lighter hypothetical particle. They were originally proposed to solve a problem in particle physics completely unrelated to dark matter. But physicists later realized that if axions exist, they would have been produced in huge quantities in the early universe, and they would have all the right properties to be dark matter. They would be very light, very numerous, and would not interact with light. The experiments to search for axions are very different. They involve using powerful magnetic fields to try and convert the axions into detectable photons. So far, neither WIMPs nor axions have been found, and the true nature of dark matter remains one of science's greatest quiet mysteries. At level 68, we have the formal name for Einstein's idea of dark energy, the cosmological constant. This is the idea that the vacuum of space itself has an intrinsic non-zero energy density. It is a fundamental property of empty space. This energy creates a kind of negative pressure, a repulsive force that is causing the expansion of the universe to accelerate. While it is our best model for dark energy, it leads to that huge quiet paradox we discussed earlier, the cosmological constant problem, where our theoretical prediction for its value is absurdly, catastrophically wrong.
At level 69, we have a beautiful piece of observational evidence that brings many of these ideas together. This is the bullet cluster. The bullet cluster is not a single galaxy cluster, but two galaxy clusters that have recently collided and passed through each other. It is a spectacular cosmic car crash.
And by observing it with different kinds of telescopes, we can see the different components of the clusters interacting. When we look at the cluster in visible light with Hubble, we can see the stars from the two clusters. Because stars are so small and the distances between them so large, they have mostly passed through each other without colliding, like two swarms of bees flying through each other. When we look at the cluster in X-rays, we see the hot intergalactic gas. Unlike the stars, the giant clouds of gas from the two clusters have collided, creating a huge shock wave and slowing down, forming a single massive cloud of superheated gas at the center of the collision. But when we map out the mass of the cluster using gravitational lensing, which detects all mass, both visible and dark, we see something incredible. We see that most of the mass is not where the hot gas is. Most of the mass is located in two large clumps that have passed right through each other along with the stars. This is the dark matter. This image is the smoking gun. It shows a clear separation between the normal baryonic matter, the hot gas, and the dark matter, proving that dark matter is a real, separate substance that does not interact with normal matter except through gravity. It is one of the most powerful and beautiful pieces of evidence we have for the existence of the invisible universe. And finally, for level 70, we have the quiet, humbling realization that comes from all of this: the unseen 95%. Let's just pause and reflect on this for a moment. All of human history, all of our science, our art, our philosophy, our understanding of the world is based on the tiny 5% of the universe that is made of normal baryonic matter. The other 95% of reality is composed of dark matter and dark energy, two substances that we know almost nothing about. We live our lives completely unaware of the vast, invisible ocean in which our tiny, visible world is floating. It is perhaps the most profound and humbling discovery in the history of science.
All right, we have explored the strange, invisible components of our modern universe. Now, for our next great ascent, we must travel back in time. We are heading to the very beginning of the cosmos itself to explore the quiet, incredible, and deeply mysterious events that set our entire reality in motion. We begin, of course, at level 71, the Big Bang. This is the cornerstone of modern cosmology. It is the theory that our universe began about 13.8 billion years ago in an incredibly hot, incredibly dense, and rapidly expanding state. It's important to remember what this theory is and isn't. It is not a theory about the creation of the universe from nothing. It is a theory about the evolution of the universe from a hot, dense early state to the cooler, larger state we see today. The theory itself says nothing about what came before the Big Bang or what caused it. It is simply the starting point of our known cosmic history. The evidence for the Big Bang is overwhelming. The expansion of the universe, the abundance of light elements, and the existence of the cosmic microwave background radiation. This leads us directly to level 72, cosmic inflation. As we discussed when we explored the great paradoxes, the standard Big Bang theory had a few problems, like the horizon problem and the flatness problem. The theory of cosmic inflation was proposed in the 1980s to solve these issues. It suggests that in the very first, tiniest fraction of a second after the Big Bang, from about 10 to the minus 36 seconds to 10 to the minus 32 seconds, the universe underwent a period of incredible exponential expansion. During this brief, violent instant, the universe grew in size by a factor of at least 10 to the power of 26. It went from a size far smaller than a subatomic particle to the size of a grapefruit almost instantaneously. This incredible stretching smoothed out any initial wrinkles in space-time, solving the flatness problem, and it took a tiny, uniform patch and expanded it to become our entire observable universe, solving the horizon problem.
After inflation ended, the universe continued to expand and cool, but at a much more sedate pace. For the next 380,000 years, it was still a hot, dense, opaque fog of plasma. The universe was so hot that electrons were not bound to atomic nuclei. Light particles, photons, would constantly bump into these free-floating electrons, unable to travel very far. The entire universe was like the inside of a star. But as the universe expanded, it cooled. And when the temperature dropped to about 3,000 Kelvin, a critical event happened. This brings us to level 73, the cosmic microwave background, CMB. At this point, the universe became cool enough for the free electrons to be captured by the protons and helium nuclei, forming the first stable neutral atoms. This event is called recombination. And suddenly, with all the free electrons now bound up in atoms, the universe became transparent. The photons that were trapped in the plasma fog were now free to travel through space unimpeded. The cosmic microwave background is the light from that moment. It is a surface of last scattering, a snapshot of the universe as it was when it first became transparent. This ancient light has been traveling through the expanding universe ever since. Its temperature has cooled down from 3,000 Kelvin to just 2.7 Kelvin, and its wavelength has been stretched from visible light into the microwave part of the spectrum. When our radio telescopes look at the CMB, they are seeing the oldest light in the universe, the baby picture of our cosmos. Just before this moment, in the first few minutes of the universe, another crucial event took place. This is level 74, Big Bang nucleosynthesis. In the period from about 3 minutes to 20 minutes after the Big Bang, the universe was hot and dense enough to act as a single giant fusion reactor. During this brief window, the protons and neutrons that had formed earlier were fused together to create the first atomic nuclei. The theory of Big Bang nucleosynthesis makes incredibly precise predictions about the outcome. The universe should have been composed of about 75% hydrogen nuclei, 25% helium-4 nuclei, and tiny trace amounts of deuterium, helium-3, and lithium. These predictions match what we observe in the oldest stars with stunning accuracy, and it is one of the strongest pillars of evidence for the Big Bang theory.
After the universe became transparent and the CMB was released, a long period of darkness began. This is level 75, the cosmic dark ages. For hundreds of millions of years, the universe was a quiet, dark, and relatively simple place. It was filled with a vast, diffuse, and mostly uniform cloud of neutral hydrogen and helium gas, slowly clumping together under the influence of dark matter. There were no stars yet, no galaxies, no sources of light at all. It was a period of profound cosmic silence and darkness, the quiet intermission between the initial fire of the Big Bang and the birth of the first stars. This long night finally came to an end with our next level, level 76, the epoch of reionization. Sometime between a few 100 million to 1 billion years after the Big Bang, the first stars and the first small galaxies began to form in the densest parts of the cosmic web.
These first objects were incredibly hot and blazed with intense ultraviolet radiation. This powerful radiation streamed out into the surrounding neutral hydrogen gas, stripping the electrons from the protons and reionizing the universe. This process happened in bubbles, with the regions around the first stars becoming ionized first, and these bubbles grew and merged until the entire universe was once again a transparent plasma, as it is today. When we look at the most distant quasars, we can see the fading fingerprints of this great cosmic transition, the moment the universe's lights were turned back on. And what were those first lights? At level 77, we have the theoretical first stars, also known as population 3 stars. These were the very first stars to ever form in the universe, born from the primordial clouds of pure hydrogen and helium. Because they lacked any of the heavier metal elements that help to cool modern star-forming clouds, they are thought to have grown to be absolutely colossal, perhaps hundreds of times the mass of our Sun. These giants would have been incredibly hot, incredibly luminous, and would have lived very, very short lives, burning for only 1 million years or so before exploding a spectacular supernovae, seeding the universe with the first heavy elements and triggering the birth of the next generation of stars.
The death of these first massive stars also likely led to the formation of the first black holes, our next stop at level 78. The cores of these population 3 stars would have collapsed to form the first stellar mass black holes. But this presents a puzzle. When we look at the early universe, we see quasars powered by supermassive black holes billions of times the mass of our Sun that already existed when the universe was less than 1 billion years old. How did they get so big so fast? It's a major unsolved mystery in cosmology. Perhaps these seed black holes from the first stars grew at an incredible super Eddington rate, feeding on the dense gas of the early universe. Or perhaps another, more exotic mechanism, like the direct collapse of a massive gas cloud, was responsible for creating massive black holes right from the start. This all leads us to the ultimate question of origins at level 79, the origin of space-time. The Big Bang Theory describes the evolution of the universe from a hot, dense state, but it says nothing about what that state came from or what came before it. This is the boundary where our current physics breaks down completely. To understand the true origin of the universe, we would need a theory of quantum gravity, a theory that can unite Einstein's general relativity with quantum mechanics. Ideas like string theory or loop quantum gravity are attempts to create such a theory, but they are still highly speculative and untested. And that brings us to the very beginning, to level 80, the singularity. According to our classical theories, the universe began as a point of infinite density, infinite temperature, and infinite space-time curvature, a singularity. But as we've learned, the concept of infinity in physics is likely a sign that our theory is no longer applicable. Most physicists believe that a true physical singularity probably did not exist, but was replaced by some kind of quantum state that we do not yet have the language or the mathematics to describe. The true nature of the first moment of time remains the deepest, quietest, and most profound mystery of all.
All right, we have journeyed back to the dawn of time itself. For this next tier of our ascent, we enter a strange and wonderful hall of mirrors. This is the realm of the great paradoxes, the quiet, looping puzzles, and the bizarre physical realities that challenge our most basic intuitions about how the world should work. We begin at level 81 with the king of all cosmic paradoxes, the Fermi paradox. As we have explored in great detail before, this is the profound and quiet contradiction between the high statistical probability that our galaxy should be teeming with intelligent civilizations and the complete and total lack of any evidence for their existence. It is the great silent question that hangs over all of our explorations of the cosmos. Where is everybody? We have explored the many possible solutions, from the idea that we are truly alone to the idea that they are hiding or that they are simply too alien for us to recognize. But in the end, the paradox remains, a quiet, humbling reminder of our cosmic solitude. Next, at level 82, we have the deep, fundamental conflict at the heart of modern physics, the black hole information paradox. This, as we know, is the battle between our two best theories of the universe. Quantum mechanics insists that information can never be destroyed. General relativity insists that information that falls into a black hole is gone forever. This contradiction has launched a 50-year quest for a theory of quantum gravity, leading to some of the most profound ideas in science, like the holographic principle. It is a quiet, beautiful puzzle located at the very edge of a black hole and at the very edge of our current understanding.
Our ascent continues to level 83 with the most famous paradox of special relativity, the twin paradox. As we've discussed, this is the story of two twins, one who stays on Earth while the other travels to a distant star at near the speed of light. Upon returning, the traveling twin has aged only a few years, while the earthbound twin is now decades older. The paradox arises when you ask, from the traveling twin's perspective, wasn't the Earth the one that was moving? The quiet, elegant solution lies in the acceleration. The traveling twin is the only one who is turned around and come back, breaking the symmetry of the situation and making their experience of time genuinely shorter. It is a profound illustration that time is not absolute, but a personal, malleable quantity that depends on your path through space-time. At level 84, we have the faint young sun paradox. This is the quiet contradiction between our understanding of stellar evolution and the geological history of our own planet. Our models tell us the sun was 30% dimmer billions of years ago, which should have left the Earth a frozen ice ball. But the geological evidence shows us that the Earth had liquid water oceans at that time. The likely solution is that the Earth's early atmosphere was a much thicker greenhouse blanket. But the paradox is a quiet reminder of the delicate, long-term dance between a star and its planet that is required to maintain a habitable world. Now we enter the realm of the truly theoretical. At level 85, we have white holes. A white hole is a hypothetical object that is the mathematical, time-reversed solution of a black hole. While a black hole is a region of space that things can only enter and never leave, a white hole would be a region of space that things can only leave and never enter. It would be a spontaneous, one-way fountain of matter and energy. While they are a valid solution to the equations of general relativity, most physicists believe that white holes are unlikely to exist in the real universe, as there is no known physical process that could form one. They are a quiet, mathematical ghost, a beautiful what-if in the world of theoretical physics.
At level 86, we encounter another famous concept from science fiction, a close cousin to the white hole. This is the idea of a wormhole. A wormhole, in theory, is a kind of tunnel through the fabric of space-time, a shortcut connecting two very distant points in the universe, or perhaps even connecting two different universes entirely.
The proper scientific name for this is an Einstein-Rosen bridge, and it is another valid mathematical solution to the equations of Einstein's general relativity. The idea is beautiful and tantalizing. It offers a solution to the great problem of interstellar travel, a way to bypass the universe's strict speed limit of light. But like the white hole, a wormhole is thought to be physically impossible, or at least incredibly unstable. The math shows that as soon as a wormhole forms, it would pinch off and collapse in on itself almost instantly, before even a single particle of light could make it through. To keep a wormhole open and make it traversable, you would need a huge amount of a truly exotic and hypothetical form of matter, something that has a negative energy density, a kind of anti-gravity that would prop the tunnel open. We have never observed such matter, and we have no idea if it can even exist. So for now, the wormhole remains a beautiful mathematical dream, a quiet what-if that lives in the equations of physics, but likely not in the physical universe itself. Let's now return to a real object for level 87, a true paradox that visited our own solar system. This is the mystery of Oumuamua. As we know, this was the first interstellar object ever detected passing through our neighborhood, and its properties were deeply puzzling. The central paradox was its acceleration. It was moving away from the sun just a little bit faster than gravity could explain. For a comet, this is normal. The outgassing of ice acts like a tiny rocket. But Oumuamua had no visible tail, no coma of gas and dust. It was accelerating without any visible means of propulsion. This is a direct contradiction in terms. It behaved like a comet, but it didn't look like one. This quiet, simple, and unsolved puzzle about our first interstellar visitor is a beautiful reminder that the universe is full of objects that will defy our neat and tidy classifications.
Our next strange object, at level 88, presents a similar kind of observational paradox. This is Tabby's star. The paradox here is the conflict between the star's identity and its behavior. When astronomers study the light from the star itself, it appears to be a perfectly normal, stable F-type star, a little bigger and hotter than our Sun. There is nothing in its spectrum to suggest it is unusual. But its behavior, as recorded by the Kepler Space Telescope, is completely bizarre. Its light dims in a way that is not only incredibly deep, sometimes blocking over 20% of the starlight, but is also completely irregular and non-periodic. A planet would cause small, regular dips. A dust cloud should produce a specific infrared signature that we don't really see. The star itself appears stable, yet something is causing it to undergo these massive, chaotic dimming events. So the paradox is this: a seemingly normal star is behaving in a completely abnormal way. The cause remains a true mystery. Is it a massive, disintegrating swarm of comets? Is it the debris from a colossal planetary collision? Is it some unknown process happening within the star itself that we don't understand yet? Or is it, as some have speculatively proposed, something artificial? The quiet contradiction of Tabby's star is a beautiful, ongoing scientific detective story. At level 89, we arrive at one of the most profound and philosophical puzzles in all of science. This is the anthropic principle, and the paradox it presents is one of fine-tuning. When we look at the fundamental constants of our universe, the strength of gravity, the mass of an electron, the energy of the vacuum, we find that they are exquisitely and seemingly miraculously fine-tuned for the existence of life. If you were to change any of these values by even a tiny, tiny fraction, the universe would have been a sterile and lifeless place. Stars would not have formed, or chemistry would not have been possible. So why is our universe so perfect? The paradox is this: is it an incredible, unbelievable coincidence that we just happen to emerge in a universe with the perfect winning lottery ticket? Or is there some deeper reason? The anthropic principle suggests it's a form of selection bias. We are here to observe the universe, so by definition, we must exist in a universe that has the properties required for us to exist. It's a simple statement, but a deeply unsettling one.
The anthropic principle is not really an explanation, but a reframing of the question. It doesn't tell us why the constants are what they are, only that we couldn't exist if they were different. This has led to more speculative ideas, like the multiverse theory, where our universe is just one of countless bubble universes, each with different physical constants, and we simply happen to live in one of the rare ones where the numbers were right for life. It's a quiet philosophical puzzle that blurs the line between physics and metaphysics, a deep question about whether our universe is a fluke or a necessity. And that leads us directly to our next thought experiment, at level 90, the simulation hypothesis. This is a paradox of knowledge. As we've discussed, the argument is a statistical one. If any civilization can create a perfect simulation of reality, it will likely create many of them. Therefore, it is statistically more likely that we are in a simulation than in the one base reality. The paradox here is one of evidence. How could you ever prove or disprove it from within the simulation itself? Any experiment you conduct, any observation you make, would simply be a part of the simulation's code. If you found evidence that the universe was made of pixels at a very small scale, that could be proof of a simulation. Or it could just be a feature that the programmers included in the simulation's physics. If you find no such evidence, that doesn't prove it's real. It just means the simulation is very, very good. It is a perfect, unfalsifiable, and looping thought experiment. It's a quiet, intellectual game that you can play with the nature of reality itself. It is probably not a serious scientific theory, but as a philosophical puzzle, it is a wonderful and humbling reminder of the limits of our own knowledge and perception.
All right. We have climbed high up our ladder of cosmic concepts. We have reached the final floor of our quiet library. Here, on this last tier, we will explore the most esoteric, the most philosophical, and the most mind-bending ideas of all. These are the ultimate questions about the nature of reality and its final, distant fate. We begin at level 91 with the multiverse. This idea, once purely the domain of science fiction, has now become a serious, if speculative, topic in theoretical physics. It's not just a single idea, but a collection of different theories that all point to the same conclusion. Our universe may not be the only one. One version of the multiverse comes from the theory of cosmic inflation. Some models of inflation suggest that it wasn't a one-time event, but that it is happening continuously, with new bubble universes constantly budding off from a larger, eternally inflating multiverse. Each of these bubbles would be its own self-contained universe, potentially with its own unique physical laws and constants. Another version comes from string theory, which suggests that our three-dimensional universe might be a brain floating in a higher dimensional space, and that other brain universes might be floating parallel to our own, perhaps only millimeters away, but completely inaccessible to us. And a third version comes from the many worlds interpretation of quantum mechanics, which suggests that every time a quantum measurement is made, the universe splits into multiple parallel timelines, one for each possible outcome. We have no direct evidence for the multiverse. It may be forever beyond our ability to test, but it is a quiet, profound, and strangely comforting idea. It suggests that reality is infinitely larger and more varied than we could ever have imagined.
From the possibility of infinite universes, we turn to the possibility that our own universe is fundamentally unstable. At level 92, we revisit the unsettling concept of false vacuum decay. As we discussed, this is the hypothesis that the vacuum of our universe, the state of empty space itself, is not in its lowest possible energy state. It is merely in a false vacuum, a temporarily stable state, like a boulder resting in a small dip high up on a mountainside. The theory goes that there is a much deeper valley, a true vacuum state of lower energy. And according to quantum mechanics, it is possible for a small bubble of this true vacuum to randomly appear somewhere in the cosmos through a process called quantum tunneling. If this were to ever happen, the consequences would be absolute. This bubble of true vacuum would expand outwards in all directions at the speed of light. Inside this bubble, the very laws of physics as we know them would be different. The properties of particles, the fundamental forces, everything would be rewritten into a new, more stable form. As this bubble expanded, it would overwrite our reality, destroying everything it touched, galaxies, stars, planets, atoms, instantly and without warning. Because the bubble expands at the speed of light, we would never see it coming. There would be no signal, no warning. One moment, the universe as we know it exists. The next, it is gone, converted into a completely different kind of reality. It is perhaps the most complete and most terrifying end imaginable. But it is also a quiet, theoretical whisper from the edge of physics, a reminder that our understanding of reality is still built on a foundation that may not be as solid as it seems. Now let's turn our attention from the potentially sudden end of the universe to its most likely and much, much slower demise. At level 93, we have the heat death of the universe. This is not a speculative what if, but the most probable endgame based on the fundamental laws of thermodynamics. It is the story of entropy, the relentless tendency of all things to move from a state of order to a state of disorder. The heat death is the story of the universe slowly, quietly, and gracefully running down like an old clock. The story unfolds on timescales that are almost beyond our ability to write down. First, over the next few trillion years, the era of stars, the stelliferous era, will come to an end. All the gas clouds will have been used up, and all the existing stars, even the longest-lived red dwarfs, will have finally burned through their fuel and flickered out. The universe will become dark, populated only by the quiet, dead remnants of stars, black holes, neutron stars, and cold black dwarfs. Then, over an even more immense period, the degenerate era, galaxies themselves will slowly dissolve as the orbits of these dead stars are disrupted over eons. Even protons themselves might eventually decay, causing all normal matter to slowly evaporate into radiation. Finally, after a truly unimaginable amount of time, even the supermassive black holes will have evaporated away into nothingness through Hawking radiation. All that will be left is a cold, dark, and perfectly uniform soup of stray photons and elementary particles. The temperature will be almost absolute zero. There will be no structure, no complexity, no change.
entropy will have reached its maximum. It is the end of time itself, because there is no longer any process that can mark its passage. It is the ultimate, eternal quiet.
While the heat death is the most likely end, there is a more dramatic, though less probable, alternative. This is level 94, the Big Rip. The scenario depends on the nature of dark energy. If dark energy is not a constant, but a force that grows stronger over time, a hypothetical form called phantom energy, then the accelerating expansion of the universe could become a runaway process. In the final stages of a Big Rip, the expansion would become so powerful that it would overcome all the other forces of nature. A few 100 million years before the end, the expansion would be strong enough to unbind the Milky Way galaxy, sending all its stars flying apart from each other. A few months before the end, it would overcome the gravity holding solar systems together, and the Earth would be ripped away from the Sun. In the final minutes, the Earth itself would be torn apart. In the final fraction of a second, the expansion would be strong enough to overcome the electromagnetic forces that hold molecules together, and the strong nuclear force that hold atoms themselves together. The very fabric of reality, every single atom in the universe, would be torn to shreds. It is a violent and complete end to everything. And that brings us to our next concept, at level 95. This is the bizarre and deeply unsettling thought experiment of Boltzmann brains. As we've explored, this idea comes from thinking about the universe in a state of thermal equilibrium, like the very distant future of the heat death. In this state of maximum entropy, random quantum fluctuations will still occur. And if you wait for a near infinite amount of time, even incredibly unlikely things will happen. The paradox is that it is vastly more statistically probable for a single small complex system, like a self-aware human brain, to spontaneously fluctuate into existence for a brief moment, complete with a lifetime of false memories, than it is for an entire, vast, low-entropy universe like ours to have come into being. This leads to the unnerving philosophical puzzle. How do you know you are not a Boltzmann brain? How can you be certain that the past you remember is real, and that the universe you see around you will still be here in the next moment? It's a quiet, dizzying thought experiment that uses the laws of physics to question the very reliability of our own consciousness and perception.
And that leads us directly to level 96, the nature of consciousness. This is not a physics problem, but perhaps the deepest philosophical and scientific mystery of all. It's what is often called the hard problem. We know, on some level, that our consciousness is a product of the complex electrochemical processes happening in the billions of neurons in our brain. But how? How does the simple firing of neurons, the movement of ions across membranes, create the rich, subjective, inner experience of being you? How does physical matter give rise to the feeling of redness, the sound of a beautiful piece of music, or the emotion of love? There is no scientific theory that even comes close to explaining this. It is a profound gap in our understanding. Is consciousness a fundamental property of the universe, like mass or spin? Is it an emergent property that arises only in sufficiently complex systems? Are we just incredibly sophisticated biological machines with the illusion of an inner life? The quiet mystery of consciousness is the most intimate and personal paradox of all. We are the universe, made aware of itself, but we have no idea how. At level 97, we have a related philosophical puzzle, the unreasonable effectiveness of mathematics. The physicist Eugene Wigner famously pointed this out. Why is it that our abstract, human-invented concepts of mathematics, numbers, equations, geometry, are so incredibly good at describing the physical universe. There is no obvious reason why the universe should be comprehensible to us or why it should follow elegant mathematical laws. And yet it does. From the orbit of a planet to the behavior of a quantum particle, mathematics seems to be the underlying language of reality. Is this just a coincidence? Or does it hint at some deeper hidden structure to the universe, a reality that is fundamentally mathematical in its nature? It's a quiet, profound question about the deep and mysterious connection between our minds and the cosmos.
Now for level 98, the nature of time. We experience time as a fundamental part of reality. It seems to flow forward, always in one direction, carrying us from the past, through the present, and into the future. But many modern theories in physics suggest that this experience of the flow of time might be just an illusion, a product of our human consciousness. In Einstein's theory of relativity, time is just another dimension, woven together with space into a four-dimensional block universe. In this view, the past, present, and future all exist simultaneously. There is no special now. Our feeling of time passing is just our consciousness moving through this pre-existing block of space-time. In quantum mechanics, on the other hand, time is treated very differently, as a universal, external parameter, not a dimension. This fundamental disagreement about the nature of time is one of the key reasons why general relativity and quantum mechanics are so difficult to unify. Is time fundamental, or is it an emergent property that arises from some deeper, timeless reality? We do not know. The quiet, familiar river of time that we feel every day may be the most profound illusion of all. We have reached our final two levels. At level 99, we have the unobservable universe. As we've discussed, because the universe is only 13.8 billion years old, there is a horizon beyond which we cannot see. But the universe itself is likely much, much larger than our observable bubble. And because of dark energy, the expansion of the universe is accelerating. This means that galaxies that are very far away are receding from us faster than the speed of light. The space between us and them is stretching too quickly for their light to ever reach us. This means that the edge of our observable universe is, in a sense, shrinking. We are losing the universe. Galaxies that we can see today will, in the far, far future, cross this cosmic horizon and disappear from our view forever. It is a quiet, profound, and inescapable form of cosmic isolation.
And now we have arrived at our final destination. We are at level 100, the unknown. This is not a concept or a theory. It is a quiet, humble acknowledgement. After all our exploration, after all our incredible discoveries, after climbing 100 levels of cosmic understanding, we arrive at the most profound realization of all, that the universe of our knowledge is just a tiny, sunlit island surrounded by a vast, dark ocean of our ignorance. For every question we have answered, a dozen new and stranger questions have appeared. The more we learn, the more we realize how little we truly know. And that, I think, is the most beautiful and most calming thought of all. It means the journey is endless. The adventure of discovery will never be over. There will always be new mysteries to ponder, new puzzles to solve, and new, breathtaking vistas of reality to uncover. So as we conclude our long ascent tonight, let your mind be at peace. Let it float in the quiet, comfortable space of not knowing. The universe is not a book to be finished, but a library with infinite, unexplored wings. And the quiet joy is not in having all the answers, but in being lucky enough to ask the questions. Let the grand, gentle mystery of it all be a soothing lullaby, a quiet reminder of the endless wonder that surrounds us. And in that wonder, I hope you find a deep, peaceful, and profoundly restful sleep. Sweet dreams.